Good morning. Chenn Zhou is a professor of mechanical engineering at Purdue University Northwest. She has more than 35 years of experience in the areas of computational fluid dynamics, combustion, energy, multi-phase reacting flows, and air pollution control, and is on the cutting edge in the integration of computer simulation and virtual reality visualization. In 2009, she established the Center for Innovation through Visualization and Simulation to integrate advanced computer simulation and virtual reality visualization technologies to provide innovative virtual training tools as well as cost-effective solutions to various real-world problems. Additionally, in 2016, she formed a National Steel Simulation and Visualization Consortium. Today, she will be presenting a talk titled, Shaping the Future of Manufacturing with Simulation and Visualization. Please take a moment to silence your cell phones, but don't put them away. We'd like you tweeting at the hashtag Dawn or Doom. Thank you.
Thank you, and good morning. I'm very excited to be here today because this was very nice event, but also the manufacture is a key to the national economy and security. And we are facing global challenges. And in order to improve the competitiveness of manufacture, we have to do something. So I'm here to talk about how to use simulation and visualization for manufacture. So I'm from Hammond, Northwest Indiana. And so what my talk will be, I'll share with you some of my personal experience, how the simulation was evolved, and what are challenges, opportunities, and I'll show a lot of examples. So let's start with a movie. Okay, how many people know what is blast furnace? Great, everybody knows how to do that. So now, when you watch the movie, I want you to think about 3 questions. How blast furnace works? Why do we need a virtual blast furnace? And how this was made, okay? So.
Welcome to U.S. Steel's Virtual Blast Furnace. This computer simulation is based on the Gary Works No. 14 blast furnace. The furnace itself is inside the building. Outside are its iron ore storage yards and support facilities, which include a skip car system, 4 hot stoves, and gas cleaning equipment. We'll talk more about these on our virtual tour. This vertical section through the blast furnace includes the burden. The orange layers are iron ore, and the dark layers are coke. Coke combustion takes place in front of the tuyeres and makes the lower part of the furnace very hot. The iron ore begins to soften and melt and forms a cohesive zone, shown in red. The gas generated by coke combustion in front of the tuyeres penetrates the coke bed under the cohesive zone, flows horizontally across the coke layers in the cohesive zone, and ascends through the burden column to the top of the furnace. Coke as it is dumped from the skip car into the receiving hopper and fills the lock hopper on the right side. The gate opens and coke is charged into the furnace through a rotating chute. The second skip car arrives with iron ore, shown in orange. The receiving hopper moves to the left, and the ore is charged into the furnace following the same steps. The coke, iron ore, and other raw materials fed into a blast furnace are called the burden.
This video was recorded in an interactive 3D virtual environment. So it's not just animation. So now you can actually get inside blast furnace from the top and look at what's going on inside. And it is a virtual environment of a real thing with a lot of scientific data. So look at that. You're now diving in through the center. You can stop any location, check what is temperature, what is CO, CO2. The color now stands for temperature. The hot is represented by red color. So now the liquid come down, start to heat up, and melt it, become liquid. So then tap out. So with this, you not only learn how the blast furnace works, but the more important is how to solve the problems. For example, the one big issue is in the bottom of the blast furnace, which is called heart. And that's erosion issue. And nobody knows what's going on inside, how the flow goes. And the erosion, if it's too much, it will kill people. We have to do the relining, spend more than $200 million. So with this, you can see, for example, the brick, carbon brick. You can get the inside, check all those data. Another issue is this. You want to increase energy efficiency. You're trying to inject some coal and natural gas to increase energy efficiency. But how to inject that? And when you inject the coal and natural gas, you burn the pipes. Look at the red color here. And they burn, you have to stop and do the maintenance. And so we actually used this solve the problem, saved $8.5 million. I'll mention that later. So now the common practice is you want to inject more coal because coal, compared to coke, is cheaper. And when you make a coke, it's very toxic. So now how to inject more coal? You got to get inside a blast furnace. You can look at all the flow properties, oxygen concentration, gas flow, particles. So anything you want to look at scientifically, but also practically, how to do the injection of natural gas and the coal. So also how the gas flow interact with those solid materials, iron ore. Look at that, when you too much goes through the middle, they call chimney, not fully utilize the gas. But if it too much goes to side, you got the erosion issue.
The gas that flows up through the burden of the blast furnace is hot and dirty.
Made? Of course, simulation plus visualization, right? So from here to there. So now, I want to talk a little bit about what is simulation in my definition. If you look around, there's so many definitions. So for our research, it's basically production of data. And specifically today, I'm going to focus on two kinds of simulation. One is computational fluid dynamics. And so basically, you have a pipe, two pipes merged together. You want to see what's, the flow field looks like, the temperature, the flow. So that's called CFD. Now, another one is called FEA, finite element analysis. For equipment, you want to know what's the stress inside, what's the lifetime of equipment, okay? So now let me focus on the CFD because that's my field. I was trained in CFD 35 years ago. So personally, I experienced the whole history of CFD application to industry. The very early days in 1970s, aerospace engineering used the CFD, okay, to save money instead of testing. But then it took long time for people to start to accept the CFD. At the beginning, people think CFD is welcome. Let me ask you, what is CFD? Do you know? Anybody know what is CFD? I was in Chicago. I was in a big building. I walked out from Art Institute and see the CFD. I was so excited. I said, wow, CFD is so important now. Guess what is CFD in Chicago? Chicago Financial District. When I teach students, I ask them, what is CFD? You know what they say? Colorful fluid dynamics, or colorful directors. So that's why I'm talking about, why people don't believe CFD at the beginning. They think this is just for, color. And some people call this garbage in, garbage out. And gradually, people start to prove. So when I work in a company, after I graduated from Carnegie Mellon in 1991, so I told my CEO, I know CFD. CFD is wonderful. It can help us save money. They said, oh, what do you need? I said, I need money to buy the software. $80,000. That time is expensive. And he was very generous. Have fun. Never took me serious. So in 1994, I joined Purdue. I started to talk to industry. CFD is wonderful. I have to back them and tell them this is so good. It almost took me 10 years to convince people CFD can be really helpful, okay? But then now, guess what happened? Almost every company trying to use CFD. And it's really, really helped a lot. But there's danger. What is danger? CFD could be garbage in, garbage out if you're not doing the validation, because there's so many uncertainties. So this February, actually, I went to a bigger convention. There was keynotes. He was so excited about CFD. He was telling people, the future of manufacturing is we can use CFD like a McDonald's. You put an order, okay, in 2 hours, you can get the results. That's the future, not yet. And that's why we need, for students, you need to start hard, and we need to do more research and development to make sure CFD can be like a McDonald's. Or another CEO told me, Chenn, this is so wonderful. I want CFD become like Microsoft. Charge your key, you get the results. No, not yet. So we need to be very careful. There's so many uncertainties, but also when you apply that into real system, okay? Just like what you saw, the blast furnace, it's so complicated in geometry. There's so many data. How do you handle that, okay? So here comes the visualization. Now, for visualization, basically, it's how to represent the data. And so for me, it's how to use visualization to represent data. I'm not a visualization expert, okay, but I'm the user. So how we use that? Virtual reality, okay? Nowadays, you have a Vive, you have Cave. So this one is our 3D theater, people inside the virtual blast furnace. This is a Vive. Actually, this is what he's singing, okay? So basically, so that's called a virtual reality visualization. Now, nowadays, there's augmented reality, and it's getting more and more popular. So what is this one? My students hold the iPhone, okay? Save the old blast furnace simulation in front of blast furnace. You push a button, you can see what's going on inside, okay? So that's still in the development stage, but that's kind of future. And this one is just Google Glass. You put the Google Glass, you see the equipment, or is this working or not? It needs to be, lock out, tag out. So this is kind of visualization we're trying to use to help the manufacturer, okay? So what we found? The integration of simulation and the visualization can be very, very powerful. It can be very efficient, effective, and economical. So for students, you all heard this statement, right? A picture is worth 1,000 words. And what are we trying to do now? Is an interactive simulation is worth 1,000 pictures and $1 million. I haven't put my name on yet. So, okay, so furthermore, what we found is this kind of integration is very helpful for learning and training. So because it creates a virtual environment, it's authentic, immersive, and we can make it interactive, engaged, and the very important is we can create a lot of real phenomena, real scenarios. It's not just animation. And you probably heard this. Oops, what is that? Okay, so you heard this. Tell me, and I'll forget, and show me, and I may remember, and involve me, and I understand. That's exactly what we're trying to do using the virtual training, okay? So in 2009, we formed this Center for Innovation through Visualization and Simulation. And this is our facility. You're welcome to visit us. It's near Chicago. And we actually use our technology to design this facility. So what we're trying to do is one keyword, which is integration. So we integrate technology, computation, simulation, visualization. We integrate the book with real-world problems. why integrate the people together? So this way we can create a virtual environment of real world problem and together with industry and to make innovative solutions. So how to do this? So basically, for the students, you all know the 3D modeling, AutoCAD, this animation thing, right? So now that one is really kind of very popular now. So you can make a geometry, but then you need a lot of engineering, fundamental, and mathematics to create the data, CFD, FEA. And the older days, you do two-dimensional. Then you need to do one more step further. You convert that into 3D type of data, and finally you make a virtual environment in VR, AR, okay? So the limitation is not basically for the application-wise. What we call the only limitation is your imagination. So we have been used this for design troubleshooting, optimization, and scale up of industry problems. And furthermore, because integration with simulation visualization, you can do facility planning, you can do logistics and scheduling, and you can also do data analytics, and the previous talk, the machine learning, and the training. And another thing is very important is safety. Okay, so let's talk about how this directly affected manufacturer side. Currently, the challenge is the manufacturer is facing aged equipment, aged workforce, and there's a lot of energy and environmental issues, and also money, okay, and how to make more new products in a faster way, how to make more new innovation. Then the big challenge is the skills gap. I'm so glad to see that young students are here. So there's big skills gap in the manufacture. So with simulation and visualization, we can actually address all those issues. So you probably heard about digital manufacture, virtual manufacture, advanced manufacture, or smart manufacture, and even Industry 4.0. So, like in Germany, they call Industry 4.0. All the things are the people trying to see how to make the future of the manufacture. And people still looking for a way. But in all these things, people know that's the kind of future, how to get there. In my opinion, in the near term, even in the future, simulation and visualization play key role, okay? So you have to start from there, somewhere. So we need to start with simulation visualization. And in the future, all this will be included. So let me give you an example. You know how to make a car? So in this car manufacture process, those are the key ones: styling, design, simulation, manufacture plan, maintenance. So if you look at all this process, actually you can see the application of simulation and visualization in every step. If you integrate this, the whole cycle of manufacture will be faster, okay, and be more efficient, and there will be also better solution. So then, in 2013, National Science Foundation, actually National Defense Industry Association made a roadmap. In that roadmap, there's key statement here: advanced manufacture modeling and simulation is a potential game changer. And now I want to also add a visualization, because we use visualization to represent the data from modeling and simulation. So basically the keywords here is a game changer, okay? So let's look at the example now. What do you solve at the very beginning, that virtual blast furnace? How it was made. It's big teamwork. It's interdisciplinary, okay? Teamwork. So what we did was basically we worked with industry, and of course the students, and experts in blast furnace. So what we did was we used CFD, numerical simulation. That is the key. You need to produce the data, all the scientific data, partial differential equation, and chemistry, okay, and physics. So then you do scientific visualization. And because you want to make sure everybody understands what you're doing, so you have to make a photorealistic 3D visualization. At the end, you make an interactive virtual process, and for training and also for problem solving. So this can be represented in VR, AR, mobile device, any and the website. So basically, each team, like industry and the research team, needs to do a lot of work. Okay, there's many, many steps involved. And so this is the challenge, is how to get all those technical know-how. From the student's point of view, you need to know technical know-how and constraints. You need to collect those real geometry, real data. Because anything, if it's not real, and it will be garbage in and garbage out. So then of course, you have to do all the CFD and the analysis, and so finally do visualization. Now, what we did, we have used this virtual blast furnace, solve the real world problem. And for example, for a company called Starco, they had an issue when you see before, when you fly into the virtual blast furnace. And this is a natural gas pipe, and this is the coal pipe. And this is a research engineer. He was trying to check what's wrong with those pipes. Do you see the red color here? The red color is high temperature, very, very hot. And when it's too hot, they burn the pipes. Then it's equipment, you have to shut down the whole furnace and to do the replacement. So basically, we used the virtual blast furnace. And he and his team originally had big arguments. Operators think this way. Engineers think that way. And the boss think another way. So no agreement. So he brought all these people into our virtual blast furnace and walking around to check the data and understand what's wrong and why it's wrong. So finally figured out how to solve that issue, and that resulted in $8.5 million annual saving and reduced downtime by 50%. Okay, we have many, many more examples like that. But another example is the training side. So this is US Steel. They do the whole day training in the virtual blast furnace. And that's including both new people and experienced people. Because again, this not just teach you how blast furnace works, but also teach you how to make it work better. Okay? So another example is reheating furnace. Basically, you have those the steel plate. You need to heat up and make a different shape. So the big issue is, I do have a movie here. So the big issue is energy efficiency and the uniform heating, the quality of the products. So what we made is again, virtual reheating furnace, and which can include CFD data, but integrate also sensor data, and also make it both 3-dimensional and 2-dimensional. What that means is you can almost do real. So we worked together, and it's used for troubleshooting and the optimization of the process. And also, everything we do, they want to use for training. So this is a Vive system. You can get inside the reheating furnace and check everything. But the more important, again, is check the data. Where's the hot? Where's the cold spots? What is the issue? What is the problem? So you can go anywhere you want. Then another example is flue gas desulfurization. So the local power company want to reduce the air pollution, okay? So what they did is they wanted us to make a virtual FGD, flue gas desulfurization simulator. So this way operator can immediately know how to operate. That's originally. But because our specialty on the integration of simulation and visualization, so they end up actually use this for not just for training at the beginning. Now they still use that the training for the emergency preparation, for the any change of operating conditions. So what do you see here now? Remember, when we made this, there's nothing there. All we had is drawings and also equipment in the parking lot. So we made this and added CFD simulation, and again, interactive virtual process. You can go anywhere you want. And what if one pump failed? How to respond that? And how it will affect the whole performance. So another example, anybody can guess what is this? For students, do you know what's this? Can you make a guess? It's hard to tell, right? But you can tell it's very, very old equipment, okay? It's a 60 years old crane in a steel company. And that crane is so huge, but so dangerous too. Because if any the equipment fail, it will kill people. So what do the company normally do? Every 6 months, they do the check, inspection. But you have to do blind check. It takes a long time, and you cannot really identify what's wrong. You cannot do prediction. So what we did is we, again, create a virtual crane. We basically did a finite element analysis. What that means, you can predict the stress inside. And also did a fatigue analysis and trying to predict the life. Then we made, again, virtual process. And so the red color, for example, is a stress, high stress area. So you want to make sure you know where's the high stress area, also where's the fatigue place, so make more crack. And because this, and now they reduced inspection time, but also they did a more target inspection. And they originally wanted to replace the whole crane because it's 60 years old. Now, because this virtual simulator helped them identify, instead of replace the whole crane, they can only replace a small part. And that is $8 million cost avoidance. And they use this for training, for safety. How wonderful it is, right? Okay, we use a similar technology, did another one. They call vertical edger in a hot strip mill. Again, you make the steel plate thinner. And that vertical edger is here, and it's get cracking all the time. And they don't know what's going on. In fact, it's one of our undergraduate student, Helen. She actually did an internship in ArcelorMittal. And she was giving me an example. You are such best bright students. You can solve our problem. She said, oh, I cannot. But our professors can do it. so they brought it to the engineers to our center. So what we did, again, the issue was, the cracking, the fail, and it delays the production, and of course, safety issue. So we did the same thing. We used the FEA, the fatigue analysis together, and we identified what's the reason for the cracking. And also we made a virtual simulator for training. And so this way, you see, again, you can identify the high stress area and also the fatigue, weak points. And so then we recommend the solution, how to avoid that. And they actually implement it, and since then, no more similar fails anymore, okay? So another example, for automobile industry, if you want to work in the assembly line, and in Kentucky system, they have called MTech. So you basically, all the students in the community college need to go through training in they call simulator, but it's a physical simulator. And the issue is, it's hard to have so many students because it's expensive. Also, you cannot break it, right? So the old-fashioned way is you use a physical simulator, and students trying to figure out a problem, they call in an old-fashioned way called a group in the dark. There's no strategy, and don't know how to do that. So what we did, we made a web-based 3D virtual simulator and included over 70 scenarios made by instructor and the industry people. And it used at over 50 technical colleges. So let's take a look. There's another movie.
AMTech is an advanced manufacturing technical education collaborative made up of over 50 technical colleges, universities, and manufacturing companies that has developed an industry-validated curriculum for mechatronics technicians. One key part of the curriculum is a troubleshooting simulator made from industry components. Civis has worked with AMTech to develop an online virtual simulator that directly mimics the behaviors of the physical simulator and includes over 70 fault-based troubleshooting scenarios. Each scenario begins by receiving a work order and choosing appropriate PPE and tools. Once on site, troubleshooting starts with talking to the operator and doing a visual inspection to identify any likely causes for the fault. Full schematics for the machine and a PLC interface are available to help trace the issue. In this case, a multimeter is used to test and identify a bad cable. The cable is replaced, and the machine is then tested to see if the fault has been resolved. Over 70 fault scenarios have been developed involving electrical, hydraulic, pneumatic, robotic, and PLC systems. Students complete the scenario by completing their work order, noting what the problem was, and any actions they took to correct the issue. Student progress is tracked to assess their performance. The virtual simulator provides unlimited opportunities for practice and enables trainees to hone their troubleshooting skills.
Is that fun? I saw the smiles from students. So this, again, this is not just a fun, it's real. And you can practice at home, in the classroom, okay? And you can make sure, train your muscle. Make sure you don't get, hurt, or you know how to fix the problem quickly in an efficient way. So now,
AMTech.
Another example is wind energy. The wind energy, again, is a troubleshooting issue, safety issue. And so this one is basically trying to use the augmented reality to look at the gears. Here, we basically made a number of wind simulators, and again, used in teaching. And we also made assessment. We found this actually increased 10% in terms of test score in the university, in engineering courses. For the technician courses in community college, and it actually increased 20%. So now, because time, I'm going to skip this one. But basically, again, it's very similar idea, a virtual simulator of real geometry and real phenomena, trying to figure out what is wrong, and based on not just animation, but also simulation data. Okay, so let's move to another one, safety. The safety is #1 in industry. And you talk to anybody from the technician all the way to CEO, they will tell you #1 priority is safety. So what is the issue? You cannot, train people in the real instance. So what we did is we actually trying to make a 3D environment to duplicate the instance, so people can suffer but not really hurt. The reason, yes, you can. My students even trying to make it like you feel hot, but not really burn your skin. So the research found authentic, immersive environment for training is most effective for safety and healthcare related. Do you know why? Because the safety training in industry, people found out 95% is because personal behavior or your awareness. You think, oh, no problem, I'm safe. Anything could happen. So if you suffer emotionally, okay, you really remember, train your muscle. Make sure you don't do things. You get a good habit, and that will work. So that's what we did is we created actually a number of simulators. For example, fall protection, lockout, tagout, arc flash, confined spaces. Those all identified top priorities for manufacture industry. And those are, the fall protection is number one. People get a fall, from height. And this one, what you saw now is a lockout, tagout in a manufacturer, plant. So the important thing is when you finish a machine, you have to lock them and also put a tag on. And people forget about that. But if anything happens, it's killing the people. It's fatal, error. So we made this one, and you can really practice. Not only you practice, you have supervisors and also your bodies, friends check with you. It's all included in the game. And also we give you feedback. How did you do? And you can keep practice until you're really, really skillful. So the steel industry highly recognize the importance of integration of simulation and visualization. Also, they really need that because the steel industry is facing big challenge for the global competition. So last year, we formed a nationwide consortium and to focus on to use simulation and visualization to solve the problems. So we identified 8 focus areas. And so those are workplace safety, energy efficiency, operation efficiency, reliability and maintenance, workforce development, environmental impacts, raw materials, and smart manufacture. So we identified the project in all those areas. And so this is showed across the whole production line, So the consortium now, we have 12 companies, including both steel producers and the suppliers. Now, what I want to come back for the question is how the simulation and visualization can be used for manufacture. So this is a kind of plot I basically imagined. So in this, again, you may have a lot of sensors, measurements. They create the data, but for us, we work very hard to use computational simulation, generate more data, because the reason is a lot for equipment, facility. You cannot get inside like a blast furnace. You cannot do measurements. They really need computational simulations to make sure to know what's going on inside. Then when you generate all those data, you have to visualize. And of course, you have to make a geometry model, then image analysis, big data analysis, and then how to make sure people understand this, how to use this in the operation or a research and development environment. And we need a 3D interactive simulator, So what I see now, we have a lot of opportunities. We also have a lot of challenges. So number one, we still have the leadership buy-in issue, the public awareness. A lot of people still don't believe you because they think it's garbage in or garbage out. Or another extreme is, this is so powerful, you can do anything, McDonald's. So we need to have a more collective, buy-in. And the second one is we need to show more successful stories. And that's what our center for, that's our consortium for. We keep telling the successful stories. We need to demonstrate. And in the industry, they need to see the value, And so then, again, you need to really, really apply simulation visualization to the real world problems, not just research in the laboratory. And so in the classroom. So then validation is still the key. No matter how advanced of the computational simulation technology or visualization, without validation, you don't want to tell people you do a good job, And you may be so excited how colorful it is, but you cannot tell people you did a good job without validation, okay? So then another challenge. You saw the virtual blast furnace. We have a whole team. Actually, we worked more than 15 years. And so in all those development stage, you need a lot of collaboration, a lot of integration, people, technology. You need a common language. So there's still a lot of challenge for that. And for students, and this is your future. If you learn modeling, simulation, visualization, definitely you can work to improve manufacture. And that's big job market because there's huge retirement, okay, in the industry. And they need not only people to work, they need a high-skilled people, okay? They need people who know the advanced technologies. And of course, the challenge, but also opportunity for computer science people, how to make computer faster, how to do more big storage, and the high-performance computing, cloud computing, all those all opportunities and the challenges. So I want to close up with another example. This is a great example how we integrate technology and people and solve the problem, okay? So anybody can tell me, what is this? Can you make a guess? What do you see? That's a real Google map. Want to make a guess? You see the chimney here? Yes. So that is emission from power plants. So the power plants, they use the coal, the boiler, to have combustion and convert that into electricity, right? So the issue they had was that there were two boilers, number 7, number 8, and they want to make sure remove the particles from the coal combustion. So they merged the two pipes, they call flue gas pipes, okay, exhaust system, into a newly installed device for air pollution control. It's great. It's regulated, right? EPA regulation. You have to meet that standard. After they install the equipment, they turn on. Guess what? Number 7, this one, lost 6% of power. So they came to us because they saw what we did before. They said, oh, we had an issue. And can you have your student do the simulation of coal combustion? That's a lot of work. That's a PhD dissertation. But remember, we want to solve real-world problem. So we worked together. We figured out approach, how to simplify this. And also, we use the simulation visualization, finish the project in 3 months. Okay? And why? That's because the power of the integration of the simulation and visualization. So let's take a look why. So before you see the movie, keep in mind, this is the flow pipes, okay, from one boiler, another boiler, and when they merge together, it's supposed to go out together, right? So the color here now, it stands for velocity. So the red color is high velocity. The blue color is low velocity. Theoretically, everybody should go out, right? So now, let's see, what is the problem
When
and
we
why?
realized we had a problem, we had a derate in the unit where we couldn't get enough airflow through the unit. We came up with different turning vane applications. We installed some turning vanes and worked our way toward the optimal solution. It was a great
Pay attention to
example
the blue
of
color.
working together very well with people who were quite motivated and eager to solve our problem. The value of the implemented solution was estimated to be $1.9 million per year. I truly think that collaboration with Purdue in this way is a tremendous win-win for both the students and the industry.
So I want to play one
We
more
realized
time.
we had a problem.
So,
we had a derate
now
in the unit where we couldn't get enough
remember,
airflow through the
the
unit.
flow should supposed to go out
We came up
together,
with
right? What do you see now?
turning vane applications.
Anybody can
We
understand what's
installed some
wrong,
turning
right?
vanes and
Let's
worked
speak
our way toward the optimal
circulation.
solution. was a
backflow.
great example of
And
working together
now we
very
solved
well
the
with people
issue.
who were,
Guess what?
quite
Everybody's
motivated
going out.
and,
See, the color is
and eager
uniform.
to solve our problem.
So why
The
we can solve
value
this
of the
problem
implemented solution
and
was
save the
estimated to be
$1.9 million
$1.9
in
million
just
per year.
3 months?
I truly think that
It's because
collaboration with Purdue
we did
was a
simulation,
tremendous
of course,
win-win
we
for
validated,
the students.
but with visualization, everybody understand what's wrong, why it's wrong, how to solve the problem, and you save a lot of time, okay? So this is the impacts we made so far for our center. Basically, we have saved more than $40 million just from 5 projects out of over 300 projects. Some of the projects I cannot tell you, it's secret, okay? But we worked with more than 110 organizations, and we had more than 1,300 students work on the problem. Every project was done by students, supervised by faculty and the industry collaborators. And so this is, again, wonderful. And we work very hard to demonstrate the application and to show the successful story. So to conclude, I truly believe the advanced technology are critical for the manufacturer competitiveness. And of course, the integration of simulation and the visualization play the key role for the future of manufacture. And that's all my talk. I want to thank all my funding supporters and also all the students who did the real work. And thank you.
We have time for a couple quick questions from Professor Zhou.
Just real quick, for the people who did walk in late, I don't think you ever defined what CFD stood for them, however.
Very good. I was waiting for you to ask that question. So, what is CFD now? Do you know what is CFD? Computational fluid dynamics. So you solve those fundamental equations based on the fundamental laws and trying to find out what's velocity, temperature inside a pipe. And normally, nobody can get inside. And it's hard to do measurements. And with this kind of technology, you can predict, for example, this room. You cannot see the airflow, right? But you can, actually, we can predict velocity in each point and the temperature. And we can visualize them. Then if you use augmented reality, you can sit there and I can see the flow around you, okay?
You talked a lot about the cost that was saved via the companies. How much did it cost to do all the work and research is my question. How expensive does that run?
Very good question. For nice thing about being a university research center, we treat this as education opportunity for our students. So for us, normally we have a whole team. In the center, we do have professional staff, but their main job is supervise students. And we make sure in the students, we have team up. The top one, of course, postdoc, PhD, master degree student, undergraduate, and even high school students. If you're interested in summer internship, let me know, okay? Especially for female students. And so then to directly answer your question, we normally just estimate the cost from graduate students. We pay them a research assistantship. So it's very cost effective. But of course, our center is self-sustained. I want to make sure, you know, I have enough money to run the center. Yes.
Let's give Professor Zhou another round of applause. Thank you.